Hello everyone, today we are going to see the reason for the colorful bubbles. The soap bubbles have a variety of colors floating through them. At times, they look like some gas giant planets. So why do these colors arise in the first place? Even though there is no color in the surroundings, we might think earlier that this might be caused by reflection. But even if there is no color in the surrounding, we still see the colorful waves on a soap bubble. Now we already know that in a rainbow, the different colors are caused by total internal reflection and refraction. So TIR and refraction inside a water droplet causes the different colors of a rainbow. But that's not the case with a soap bubble. The soap bubble is a thin film of soap which has air on its two sides. The outer and the inside of the soap bubble, the outside and the inside of a soap bubble have air. So the different colors of the soap bubble actually owe to the phenomenon called interference of light. So when we think about interference, we always think that there must be two surfaces or two sources of light rather. So the two sources of light should be interacting with each other in some way in giving constructive and destructive interference. So this is a thin section of a soap film. So we are looking at this magnified. Okay. Now the soap film, let's say refractive index N, mostly this is water, so the refractive index is 4:3, has air on its two sides. So refractive index of 1 on its two sides. So this is rare, this is rare, this is denser medium, this is optically denser medium. Now when white light falls on this film, let's draw a normal here. Now when white light falls on this film, this is the incident ray, the angle of incidence. So on the first incidence itself, the ray splits into two parts. Some portion of the ray is reflected back into air and some portion is refracted through the glass film. So this is the refracted ray. Let's draw the angles here. So this is angle of incidence. We know the angle of reflection is also equal to the angle of incidence. So this is I as well. This small angle is the angle of refraction. So even at this second surface, once more, a portion of light is reflected and some of it is refracted. So refracted back into the air. So this goes away from the normal. Now this reflected ray, which is reflected from the inner surface of the soap bubble, comes out at the same angle as the ray which came out at the first reflection. This follows from the Snells Law. That says n and sine of the angle with the normal is constant for various media. So for some specific ray, this product remains constant. So this is our Snell's law. So these angles, the angles with the normal, this angle and the angle with the soap film itself are the same for these two rays. Okay. So here we can see we have two rays now coming out of the soap film or coming away from the soap film. So these two rays, they behave like two sources, S1 and S2, like that in Young's double slit experiment. So if we have a screen here, we have an interference pattern here. Now, this interference pattern is pretty much the same like that in Young's double slit experiment. So here we would have some central fringe, then we'll have separate bright and dark fringes. at a specific point, let's say on this point, the distance x from the soap, horizontal distance x from the soap bubble, at this specific point, some ray would be making constructive interference. So at the constructive interference, that some specific color is visible to the eye. So the criteria for constructive interference, we know that the path difference R2 minus R1, the path difference between the two waves should be n lambda. This is the path difference. This plus this is the path difference between these two waves. So we have two sources, we have two waves coming off a soap bubble. This is often termed as thin film interference. This entire phenomenon is thin film interference. So a thin film gives two sources of light from a single source itself. These two sources are separated by this much distance. Now what is this distance? Let's calculate this. This is the path difference, because this very ray, this ray goes directly here, and the refracted ray covers this much of extra distance. So we got to calculate this extra distance. So this extra distance will give us the path difference between these two waves. Okay, so let's do that. So in this triangle, we want to find out, so let's name the points A, B, C and D. So we want to find out AC plus CD, and we can see from the geometry that AC and CD are the same thing. So the path difference actually R2 minus R1 is AC plus CD, that is twice AC. We have a relation of cosine of the angle of refraction here. So cosine of R is AB, meaning the thickness of the slab. Cos R is the thickness of the slab divided by the hypotenuse, that is AC. Therefore AC is the thickness divided by cosine of R, cosine of angle of refraction. Okay. So the path difference we get here, R2 minus R1, is twice T divided by cos of R. This is the geometrical path difference. So this is the geometrical path difference, geometrical delta x. But here R2 minus R1, we need to find out the optical path difference. So by optical path difference means actually how much of a difference is there between the waves. So the optical path difference is n times the real path difference. So the real truth is light travels n times slower inside this entire region. Inside the entire glass film region, light travels n times slower. So instead of that, we think that n times extra distance is covered. Whatever distance is covered inside this region, we multiply that with n. So that gives us the optical path. So the geometrical path difference obtained here is this. So the optical path difference, R2 minus R1, actually the difference between the light rays optical, this would be 2 nt divided by cos R. So this much of an extra distance is covered by the second ray before coming out of S2, before coming out of this point. This much of an extra distance is covered. So S2 minus S1 or R2 minus R1 gives us the path difference, gives us the condition for constructive interference. But we have one more catch here. At first incidence, our light ray is traveling from a rarer medium to a denser medium. Now whenever this happens, there is a path difference in this light itself of lambda by 2. Like we can see this in this side region. If this is a light ray incident here, then the reflected ray will have a path difference of lambda by 2. The reflected ray is said to be phase reversed. The phase changes by pi. This happens whenever the reflection occurs from a rare medium to a dense medium. So this has already changed the phase by lambda by 2. Sorry, the path by lambda by 2. So the phase is reversed by pi. So the condition of constructive interference, instead of n lambda, the regular constructive interference, we get half added to it. So this n is an integer. Let's call it m here. So m stands for an integer. So n is the refractive index of the soap film. So the condition for constructive interference of this, instead of n lambda, it becomes n plus half lambda, which in general case is the constructive of destructive interference. So this half lambda is added because of the phase reversal at the first incidence. At the first incidence, light travels from a rare to dense medium. That is why a phase reversal happens. This phase reversal does not happen when light travels from dense to rare. When the reflection happens from dense to rare, like in the second point, there is no phase reversal. So here we do not have any phase reversal, because here the reflection is happening from dense to a rare region. Okay, so this is the final condition for constructive interference. So we take this as m. In most of the cases, the thickness of the film is so less. It's obviously the thickness of the film is so less that the angle of refraction itself becomes negligible. Now, since the angle of refraction is negligible, cos r becomes 1. When r tends to 0, cos r becomes 1. So we get this relation 2 nt is 2m plus 1 lambda by 2. That is odd multiples of lambda by 2. Therefore lambda becomes 4n times t upon 2m plus 1. So what all wavelengths satisfy this condition, the wavelengths that satisfy this condition, form a constructive interference at that point. So there would be some waves. Let's say, for example, the red colored wave satisfies this condition here. So both these rays meet here and we observe a red colored light here. Maybe a blue colored wave satisfies this condition at this specific angle. So at this specific point, we see a blue color. So at different places, different colored waves, rather different waves from constructive interference and different waves from destructive interference. So the destructive interference colors are absent from the film and only the constructive interference colors are present at those specific angles. Okay, so the interference phenomenon is responsible for different colors inside or different colors coming out of a soap film. The two sources have the two waves. The path difference is created by the soap film itself. So this is the first ray, this is the second ray, and this is the path difference AC plus DC. This is the equation for constructive interference. Obviously the equation for destructive interference would be two nt would be equals to n lambda, m lambda. So this is the condition for destructive interference. So these colors, these wavelengths are absent at that very specific point. Okay, I hope this is clear. So the reason for different colors of a soap film inside a soap film is interference of light and not any other phenomenon. Okay, I hope this helped. Thank you.